Hello, I'd like to share with you our research on learning morphological and inflectional paradigms from interlinear gloss text. And the big picture behind the motivation for this task is the fact that many low resource languages take a long journey to be accessible to NLP research, and we'd like to shorten that journey. So as a case study, we've chosen morphological inflectional paradigm learning. So if you think about in English, a verb like read, we can have forms read, reads, reading, read, just 4 forms. Here's a Polish verb for read, which has many more forms than that. And so learning all of these inflectional forms is quite complicated. And we are replicating a shared task from the Sigmorphon shared task, which feeds the data either a lemma or, as you can see here, another inflected form, some morphosyntactic features, and then trains the model to learn to generate the correct inflection form from those features. So the past tense of grips is gripped, and the lemma of grips is grip. So it's generating an arbitrary member of a paradigm given another inflected form and some morphological feature description. The Sigmorphon task usually use curated data from published text or from Wikipedia, which is clean and has gone through many steps. It's taken that long data journey. We are trying to do this from interlinear gloss text, which is a very underutilized resource in NLP, although it's one of the few resources available for a large fraction of the world's languages. It's one of the first things that linguists do, analytical tasks that's undertaken after a language is transcribed from a recording. However, there's some issues that have to be dealt with that don't appear in polished publications. It's inconsistent, so the data has a lot of noise, and in part this is because it's produced through ongoing analysis. So it's changing as a linguist learns more about the language. Secondly, it has no part of speech tags. The basic interlinear gloss text just has 3 lines underneath the transcribed sentence. So you have a line where the words are broken into their morphemes, then you have the gloss or strict translation of those root morphemes and of the affixes, which are in capital letters by convention, and then a free translation. So no part of speech tags, which is an issue for trying to recreate the inflection or reinflection shared tasks, because as you can see, those have part of speech tags. Here in the morphosyntactic features, the V stands for V. So first of all, we wanted to see what effect this would have. So we reran this shared task with 10 with languages which cover a broad range of structures and families, with and without the part of speech tags. And I don't have time to go into the details, but just a glance at the data shows you that most of, showing the differences here, you can see that most of the time it's less than 1 percentage point in accuracy. So by that, we feel safe to conclude that part of speech tags actually don't make a significant difference in this learning morphological paradigms. The second issue was the noise. So right here we have data in the Lesgi language that was automatically generated. The paradigms are separated by empty lines. After we automatically generated, we wanted to deal with a noise. So we ask language experts to go through and clean the data. But instead of, again, taking many months or years that it would normally take to prepare data for NLP, we asked them to limit their time. So they spent no more than 7 hours cleaning up the data, which you can see on the right, the results from this particular data. And you can see some of the issues that they took care of. So because of how we extracted the data based on the glosses, we actually had inconsistent glossing. So instead of 3 paradigms, this is actually 1 word. So it's 1 lemma. This is 1 paradigm. They also corrected typos, and also there were some incorrect glosses, which they caught and corrected as well. So from that cleaning process, we took both the noisy and the clean data, and we ended up with some training data. So we started with the total number of annotated or glossed words in the data. And for each of the languages, we ended up with this many paradigms in both the clean and the noisy data. And all 5 of these languages, Arapaho, Tses, Lesgi, Manipuri, and Natugu, are under-resourced, under-documented, and not all minority languages. Manipuri, for example, is spoken by about 1 million people in India, but it's not a national language. So with this many paradigms, we generated our training data by taking a random inflected form from each paradigm, and then the morphological features of all the other forms and pairing it with that word. And then we generated all possible pairs in the paradigm, which gave us this amount of training data just from that. On top of that, we wanted to address the minimal resources with some techniques that have proven useful in other low resource languages. So we took also the unannotated data, so the data that was not glossed, and we used that to augment it, to kind of reinforce the model's ability to learn the structure of words. So you can see that on the right here, where we just took these unannotated words, and the morphological features then, since we didn't have any, were just 4 X's to represent them. We also tried another successful data augmentation, the data hallucination method, which has been successful in other tasks, where basically artificial stem morphemes are generated. You can see that there in the red, but actual inflectional affixes are used. So it reinforces the model to learn the inflectional morphology of the language. And we generated 10,000 artificial examples for each language with this second method. And we, with both the clean data and the noisy data, and with all the augmentation methods, and we also combined the 2 augmentation methods, we ran each of them through 2 processes. So the noisy data was trained on transformer model to generate missing inflected forms. And then the data that had been cleaned by an expert was also trained another model and also asked to generate the same missing inflected forms. And then we compared the results to see what we could do with this data that came from field data, interlinear gloss that was produced by linguists on the field. And again, just to remind you, we're choosing a random inflected form, morphological features, and generating the correct inflected form from those features. So the past tense of grips would be gripped. That's the one that's missing here. And here are our results. So we actually compared it with an LSTM-based sequence-to-sequence model with exact hard monotonic attention, but our best results were achieved by the transformer, so that's what I'm showing here. One of the first things that we can notice is the relatively low performance of Arapaho, even with this drastically more data. So I've copied the amount of training data and total number of words there on the left. It has drastically more data than the rest, but its results are actually worse than it says. And it's probably or possibly due to the fact that Arapaho is a polysynthetic language, so it's much more morphologically complex than the others, which are agglutinative. Another thing we notice is there's no clear correlation to the size of the training data and the results. That's particularly noticeable. So there's the Arapaho results. And if we look here at Lesgi and Manipuri, there's a big difference in the amount of data they have, but the one with more data actually has poorer results. If we look at the improvements after cleaning, we see the biggest improvement in Lesgi, which is probably due, based on our observation, due to the fact that it was the most noisy and inconsistently annotated data. We see less improvement, for example, on the last line than Tugu or that says above the Lesgi, which may indicate that if you have really clean data, you don't need to spend the time to clean it more. It's kind of a decreasing return of investment. It also seems that the noisiest data, if we measure it by the greatest improvement after cleaning, do not benefit from augmentation, do benefit the most from augmentation techniques, which we can see with Lesgi and Manipuri, had the greatest improvement after cleaning, and also were the ones that definitely benefited from the augmentation techniques. So as in conclusion, research questions were whether interlinear gloss text from field linguists could be used for NLP and morphological paradigm learning. And the answer we found out is yes. The results aren't great, but they're definitely promising with such limited data. Whether the part of speech information is useful for this task, which we find out not really, and whether a few hours of annotation by a language expert helps and improves data, which it does. We also found that data augmentation methods based on these few languages seem to be most effective for very noisy data. For future work, we'd like to examine closely the surprising result that PO part-of-speech tags don't seem to be very helpful, and also to use this method of going from IGT or interlinear gloss text to paradigms to then assist linguists in automating their glossing methods, which in turn will increase data for NLP task. In conclusion, I'd like to acknowledge the linguists who provided the data and help us clean it.